Ladies and gentlemen, good afternoon. It's a pleasure to have you here in our workshop, The Potential of Closing the Carbon Cycle in Chemical Industries. We will have two presentations by Alexis Fasanella and Thomas Bayer, followed by about 30 minutes of discussion. So please prepare to contribute by comments or questions. You may raise your hand or use the chat room. I will moderate this workshop. My name is Manfred Kircher. I'm a freelance advisor on bioeconomy with a strong background in chemical industries, partnering and cluster management. One of my current jobs is co-chairing the innovation space BioBall, or bioeconomy in metropolitan regions, that will be presented in this workshop later. Now, I'd like to give you a short introduction to the workshop. Climate protection and the burdens of European emissions trading demand the avoidance of greenhouse gas emissions. While the conversion to emission-free energies is possible and on its way, the emission potential from the carbon bound in chemical products will remain in the long term. One way out is to close the carbon cycle by creating circular value chains using, firstly, photosynthesis, secondly, recycling, and thirdly, carbon capture and usage, or CCU. This session presents the status quo and future scenarios of carbon recycling for the chemical industry up to 2050. And especially this topic will be presented by our first speaker, Alexis Michael Fasanella, who is head of research and project coordination at DECHEMA and has 20 years of experience in the initiation and management of research and innovation programs. On his track record are research programs and projects on carbon capture and utilization, including the 100 million euro German BMBF funding program on CCU in 2010. And he's the author of several discussion papers and technology studies on power-to-X, CO2 utilization, carbon processing technologies, and GHG saving potentials of the chemical industry. The latest public study is the Roadmap Chemistry 2050 for the Association of the German Chemical Industry, VCI. Alexis graduated in chemistry in 1994 and finalized his PhD in analytical chemistry from Technical University Darmstadt in 1998. Alexis, the floor is yours.
Thank you very much for the kind introduction. Okay. Okay, I can't share my screen because you're still blocking it. So if you unscreen, that's okay. Necessary.
This is good.
Otherwise, I can't do it.
No, it's not me. There's another screen shared.
Okay.
I'm sorry.
Just saying I can't share the screen. I'm sorry.
I'm sure in the office they are already working on. You may start with some introductory words.
I can do. Okay, of course, without slides, that's a bit difficult, but I try my best. So I'm trying to give you some main conclusions of our study for the BCI Roadmap 2050, looking at different technologies for carbon neutrality of the chemical industry. Now, slides would be perfect, actually. Is our technical support still in the room?
You may explain the background of this study.
I can do this, of course.
Participating and how was it organized?
Yeah, it's a study that we, DECHEMA, will have been doing with another company, Future Camp consultancy in Munich. This was accompanied by a panel of industrial representatives from chemical industry, mainly petrochemical industry, that were supporting us in well, in the assumptions, in the discussion of different technologies we were taking up in the study. So in the end, this was about creating a portfolio of different technologies and setting up different scenarios or pathways to describe greenhouse gas neutrality by 2050. Now it seems I can share my screen.
No.
Can you see this now?
Yes.
Okay, that's better. Okay, just as a short introduction, so what does the chemical industry do essentially? So chemical industry needs fuels and electricity, so energy, and also feedstocks that are converted in a chemical process to process. And with this, we have three different sources of CO2 emissions, essentially. So the one is energy-related emissions, so the carbon emissions from the burning of fuels, but also from the carbon footprint of electricity that is used. We have process emissions, so non-energy related emissions, where CO2 is a byproduct in the chemical process. So that's quite unique for the chemical industry. It's also the case for cement industry, for example, where CO2 is also part of the process. And of course, we have, in the case of organic chemistry, products containing carbon. And these, at the end of their lifetime, will also cause emissions of CO2. And if we briefly look at the numbers for Germany, we've been looking at in this study. So we are talking about roughly 190 terawatt hours of energy, of which 54 terawatt hours are electricity, 20.8 million tons of feedstock, or translated to carbon feedstocks, that's around 18 million tons. And then you see the different shares of carbon or CO2 emissions here. What we've been doing then is a complete accounting of the carbon emissions. And so scope 1, 2, 3, so process and energy related emissions, emissions that are caused by the well, power sector, so the supply of external electricity and district heating, and emissions also that are caused by the carbon content of the product of the products. And this is actually something that is new, that has not typically been taken into account by the chemical industry when they talk about their CO2 emissions. And then we were looking at three different pathways: reference, which is, so to say, state of the art or business as usual; technology pathways, where we start to implement technologies, low carbon technologies; and greenhouse gas neutral pathway, where greenhouse gas neutrality is enforced. So this is in a nutshell the results. If you look at the greenhouse gas reduction potentials, and you can see in the 2020 figure already that the scope 3, so the product related carbon emissions, are around half of the total CO2 emissions, and these are the ones which are also the most difficult to get rid of. So you can see that the scope 2 emissions by external electricity will already vanish in the reference pathway, and this is due to the decarbonization of the power sector, which will be, if the political ambitions are followed, will be completed by 2050, more or less. And for the scope 1 and scope 3 emissions, however, we need to close the carbon cycle. So we need to avoid the use of fossil feedstock and energy carriers, and to replace that by alternatives. And brief look at the potential alternatives you see here. So on the one hand, we have to base our energy supply on renewable electricity. So this not only includes the electricity supply that is typically the case in chemical industry, but also the formation of heat, which is typically done by burning of fossil fuels. So this is also to be replaced partly by electricity-based processes, so power to heat, essentially. And in terms of carbon sources, this is what we have as alternatives. So we have industrial CO2 or carbon monoxide emissions. We typically talk about industrial symbiosis in this context, for example, off gases from steel industry. Of course, we can also use CO2 from air by direct air capture, but this is much more challenging because of the low concentration of CO2 in the air. We have biomass as the second option, as renewable carbon feedstock. Of course, we need to take care that we are not addressing feed and food biomass. So we are also talking about waste biomass here. And of course, we have other organic carbon containing wastes, and essentially waste plastics are an important source here. And this is where the term of circular economy or recycling of plastics comes into the game. So in the study, we've then been looking at different technologies at sufficiently high technology readiness level to be implemented by 2050. And our main focus was on base and petrochemicals here because they cause the major share of CO2 emissions of the chemical industry. So we've been looking at chlorine, at ammonia, urea, methanol, the low olefins, so propylene, ethylene, and the BTX aromatics mainly. And we can see electrolysis-based processes, so electrolysis of water and then the subsequent synthesis process. We can also see pyrolysis of methane as another option. We see biomass-based processes, for example, for methanol. We can also see the chemical recycling of plastics by pyrolysis or gasification as a sort of replacement of naphtha for steam cracking. So this is essentially the portfolio. I'm not going to discuss this or introduce this in much detail. I rather want to show you the effects here, but don't get scared of this seemingly complex figure here. It shows the main milestones or decision points when we look at the implementation of these technologies. So what you see here is conventional methanol production. That's the black lines versus methanol via electrolysis hydrogen. So that's the red lines. And we see specific production costs and we see CO2 emissions. And the vertical blue lines show the decision points or the main milestones. So TRL9 means at this point in time, the technology, the new low carbon technology will be ready to be implemented. And this will be around 2030 in the case of the methanol production. The next decision or the next point is when the specific CO2 emission of the grid electricity cross actually with the specific CO2 emission of methane steam reforming. So this is the earliest point in time when using electricity-based processes will lead to lower emissions compared to the fossil route. Of course, this is important. Before this point in time, it doesn't make sense from a greenhouse gas emission point of view to implement these technologies. And now you see the more challenging point is the production costs. You see that the production costs for the fossil route, that's the black lines, the black line or the dashed black lines, they increase over time. This is just because we assume that we have rising CO2 abatement costs, for example. And the specific production cost for the red line, so this is electrolysis based, will decrease over time. And the intersection is if we look at non-depreciated plants, so implementing of a new plant with the new technology compared to a new plant of the reference, is only in 2044, so relatively late, and even more later if we compare this new plant with the existing depreciated plant. Unfortunately, this is the realistic scenario, because we don't have any greenfield investments in petrochemical plants in Europe or in Germany. So we have to compare the new implemented plants, and you see this is relatively close to this deadline of 2050. And of course, we can influence this point in time. So just a brief look at the cost sensitivity of the production. And you see we have a strong dependence of the electricity costs, which is quite typical for an electrolysis-based process. So the lower the price of electricity, the lower, the earlier is the implementation time. And the total opposite is the fossil fuel price, because that determines the cost of the fossil reference process. So these are the two contradicting points. So we need higher prices of fossil fuels and feedstocks, and low prices of renewable electricity mainly. There are some other factors, but I don't want to go into details for that because of the time constraint here. But keep that in mind, these are the two main factors. Then we can look at what do we need to implement these technologies to achieve greenhouse gas neutrality. And you see that we have a strong increase in the demand of electricity here. So this in the greenhouse gas neutrality pathways goes up to around 680 terawatt hours. So that's 12 times the amount of the 54 terawatt hours we have today for the chemical industry in Germany. So huge increase in electricity demand. Of course, we need CO2. A lot of CO2. That's around 43 million tons in our in the scenario we've calculated. So this is still feasible if we have industrial sources available. Even if we run out of fossil power plants, we still have steel industry. We still have cement industry, for example. One slide on plastic recycling, at least. We've been looking at the typical non-energetic recycling routes, so mechanical recycling and chemical recycling here. And of course, if we do mechanical recycling, we're more using the more pure and clean plastic waste fractions from production waste, for example. And this is a sort of material recovery which will replace part of the virgin plastic material as a recyclate. For chemical recycling, we're replacing parts of the monomers, and this is more challenging. So this is something where we can use mixed and also contaminated plastic waste, so post-consumer waste, for example. And we've done a very conservative calculation on the basis of some data that Plastics Europe in Germany gave us in terms of the available plastics amount. And what you can see is that we can replace around 1.2 million tons of olefins by using plastic waste. You can debate this number. It's conservative in the amount of plastic waste we're using. It's ambitious enough in terms of the technical development of the recycling technologies. So to summarize, a few points that will determine the opportunities and challenges for the transition of the chemical industry. So first, the good news. So we have new technologies at hand that would allow us to reach the target of greenhouse gas neutrality in 2050. But there are a few restrictions. We will cause a very strong increase in energy demand, and in particular electricity demand. We also see that we will have a significant increase in the production costs. So there's still an economic gap of these new technologies because of the more costly feedstock in case of biomass, or the high electricity costs. And of course, also in investment. So we calculated around 70 billion euros for investment needs in Germany. And this is mainly because we can't retrofit existing plants here. So we have to install new plants based on these new technologies. Of course, we still need research, development, and innovation. For example, to get to higher efficiency of chemical recycling, which is today at relatively low 46% of carbon efficiency, if you look at pyrolysis and gasification. And we, of course, also need to work on scale-up and serious manufacturing of electrolyzers to really get these to an industrial scale. What also has to be considered, and I can't discuss this in detail, perhaps we can do this during the discussion, is questions on logistics, for example. So plastic recycling, of course, needs a lot of logistics, but also the question, do we still keep centralized production plants, or will we more move towards decentralized production where we can have better access to, for example, CO2 and renewable electricity compared to a central setup. So these are also elements that will determine the question of the transition of the chemical industry. And with that, I hope this was not totally overwhelming to everyone. I had to put in some material in a very short time. So thank you for your attention, and happy to receive questions later.
Alexis, thank you very much for this extremely informative and visionary presentation that may provoke indeed an intensive discussion. We have already one comment in the chat. We will address it in the discussion later on. Before I invite Thomas Bayer to the floor to present his view on industrial strategies to sustainable carbon sources. Professor Dr. Thomas Bayer is Vice President Research at the Provades School of International Management and Technology in Frankfurt. He has more than 30 years of experience in chemical and pharmaceutical industry in development and production, and in several national and European funded projects. He is the co-initiator of the BioBall innovation area. BioBall means bioeconomy in metropolitan regions. And he's chairman of the association BioBall. Thomas graduated in chemistry in 1984 and finalized his PhD in bioprocess engineering from University Hannover in 1987. Thomas, the floor is yours.
Yeah, thank you very much, Manfred, for your kind introduction, and a warm welcome from my side too. So, in fact, everything heard from Alexis about the chemical industry in Germany, and that everything is possible to reduce carbon dioxide emissions, with some buts, right? So, but what does it really mean if you're coming a little bit closer to an industrial site, for example, like a chemical park? So what is going on today in these chemical parks? What are the ways to get CO2 neutral in 2050? So what could a chemical park offer to come closer to these goals? And first of all, there's a lot of infrastructure. And of course, there are power grids. We supply in these industrial parks the different customers with electricity and of course with heat, mainly in the form of steam. In a lot of different chemical parks, hydrogen is still available. And of course, disposal in any case is an issue. So for example, some industrial parks still have the possibility to produce biogas from wastes, or are working on phosphate recycling. So there are a lot of different interesting projects running, which is a little bit dedicated to circular economy. And beside infrastructure, of course, you could use these existing infrastructure as a kind of innovation campus. This is especially what is done in the industrial park in Höchst in Frankfurt, Germany. So, of course, you can bring all different startup companies, investors, universities, whatever, to work in maybe funded innovation projects and to settle them in a kind of containerized plant or whatever, to develop in an industrial scale plants to produce power or use power and carbon dioxide to produce gases, liquids, or even chemicals. And of course, industrial parks still have a lot of networks because they have a lot of companies normally running in these sites, and you can bring in all these different expertise into these projects to get closer to a carbon CO2 neutral chemical industry in 2050. And of course, because we are located here, this is our example, the industrial park here, Frankfurt Höchst, which is a space, let's say, not far away from where Alexa's beautiful background pictures made from downtown of Frankfurt. And of course, the largest airport is very close to our site here. And in total, we have more than 4.6 square kilometers inside, mainly located on both sides of the River Main. And of course, close to 1,000 rental buildings are located here, and about 90 companies producing chemicals, pharmaceuticals, everything from plastics to agricultural chemicals and so on. And of course, we have 120 production plants here on site. And these kind of conglomerates in industrial parks are still consumers of electricity and of heat today. So with 22,000 employees working here, the companies in the industrial parks are consuming about 1.5 terawatt hours of electricity. And if you maybe remember, the electricity consumption in Germany is about 500 terawatt hours. So it's a huge consumption of electrical energy. But still, these sites are not mainly driven by the consumption of electricity. They are more driven by the use of heat, normally in form of steam. And the use of heat, the consumption here in the industrial park is close to 4 terawatt hours, which is more than 2 times of that what is consumed in form of electricity. And if you compare that with the whole heat consumption of a city like Frankfurt, it's mainly 30 to 40% of the whole consumption on heat compared to the whole city of Frankfurt. So how is that produced today? And in industrial parks, you very often have your own energy supply and your own energy network, because you could use, example, heat from chemical plants. If you have exothermic reactions, you can inject these in form of steam in the network in your plant site, and you could use it in other plants with endothermic reactions. So it's a network to produce electricity. And of course, we are incinerating gas and coal today, but we are still using heat from a sewage sludge incinerator with a capacity of about 200,000 tons. We have a biogas plant here with a hydraulic throughput of about 400,000 tons. We have a biogas upgrading plant to produce biomethane for the national gas grid. And of course, we have a refuse-derived fuel plant with a capacity of more than 500,000 tons. So in any case, we're trying to produce the electricity needed on site and even the heat on site. And a little bit different to what the German federal government decided, we are not planning to run our coal-fired power plants until 2038. We want to reduce the usage of coal this year, so meaning that we want to start next year with new gas turbines and shut down our coal-fired boilers. So we are investing 3 digits of millions in new, even with natural gas-fired plants. Of course, you can produce electricity and heat from these new plants, but still we can use the flexibility of gas turbines to stabilize the national electricity grid, which is even an issue today in Germany. And of course, another issue is, of course, you can't even shut down the most of the chemical or pharmaceutical production plant. They have to run all over the day, all the days per year. So you have to make sure that you can supply them with heat and especially with electricity. So you have to have a kind of startup capability too, and a kind of autarky in these industrial parks. And of course, we installed several years ago, 6 or 7 years ago, what is called electricity to use to produce steam, even to stabilize the national electricity grid. You can get electricity with very low price to produce heat in the industrial park. And this could be done in summer, even as in winter time, because we are using steam all over the year for our production plants. And of course, we are expanding our connection to the national electricity grid to make sure that we can get in future, hopefully, carbon neutral electricity, because we think that we have to transform a lot of chemical processes to use more renewable energy and form electricity. This is more or less what Alexis showed us in his lecture here today. So we are trying to prepare ourselves in the industrial park, therefore. So if we are looking in a lot of industrial parks or chemical sites, you even have available hydrogen today. And the hydrogen is used, for example, for a lot of customers in the industrial park for classical hydration reactions, but even for customers outside. So we have a grid for hydrogen within our chemical site of different pressure levels and in a length of more than 20 kilometers. And of course, we are kind of hub in the Rhine-Main region with trailer stations here on 200 and 300 bars. And of course, we have for more than 10 years, since 2007, a fueling station here for hydrogen on 350 and 700 bars to fill cars, trucks, and even buses. And today, bus lines within the industrial parks are running with fuel cell buses. And of course, for the moment, we are preparing a station to fill hydrogen fueled trains, which are running in the regional transportation here from the Rhine-Main Association. And even here, we are using much more hydrogen compared to buses or cars. So we are talking here about 1 ton per day to fill these trains. So we are connecting to the infrastructure in the surrounding community, and we are trying to support the mobility with carbon neutral transportation. And of course, there's a lot of stuff available. Even Alexis mentioned that, of course, you can try to get the carbon dioxide from the atmosphere, but this is still very energy consuming. And of course, a lot of carbon dioxide is produced from chemical reactions as a byproduct. And from my understanding, some incineration plants, like example, sewage incinerators will be running still after 2050. So we still have some points where we get carbon dioxide in a higher concentration, easier to catch. So we can use carbon dioxide, we still have hydrogen, we have biogas, we have energy and all this stuff to do all these kind of projects here to produce fuels, methane, chemicals, hydrogen, and whatever, even in a first amount of material. Maybe not to fulfill all the needs of the chemical industry, but we can run our industrial park here as a kind of innovation campus, because it's very easy to install here these kind of projects to get in a kind of industrial scale with these innovative ideas, for example, to produce chemicals or liquids for the mobility side or even for chemical companies. And of course, another issue is to connect the industrial parks with the outside world, meaning with the surrounding. And Manfred mentioned the BioBall initiative, which is using wastes even from an urban area here to better understand how to convert that. What is normally done today is to use more or less the wastes to produce power and energy. And we are trying to shift that a little bit more to use wastes to produce chemicals or even other feedstocks for the chemical and surrounded industry, or even for some raw materials to produce materials, food, or so on. So we're trying to connect to our urban neighbors here. So an industrial park is not only some single point, but it is connected into the surrounding area. And due to the time, this is all I want to show here. What does it mean to get from, well, the German chemical industry could be carbon neutral in 2050? What are the first steps we have to do in industrial parks and larger chemical companies? So thank you very much for your attention, and well, open and looking forward to your questions.
Thomas, thank you very much for giving us this impressive view on a chemical production site by the example of Frankfurt Höchst, stressing the role of such a site in turning innovation into industrial reality. Now the discussion is open. We have 22 participants in this workshop, and I like to encourage the audience to place comments on the chat. I'm not sure whether raising the hand is working because I can see only the presenters in the list of participants. So I like to encourage you to use the chat. We have already one comment in the chat. This was given very early in the presentation of Alexis. And this was a question about the role of hydrogen. I think both of you addressed hydrogen already, but you might explore more in detail the role of hydrogen in the future and how to provide it. Alexis, would you like to?
Yeah, okay, of course. I think perhaps I was too fast in providing the list of technologies, but hydrogen is absolute key in most of the processes we've been looking at. So, but I have to be more precise. So hydrogen in this sense as an intermediate and reaction partner for CO2, for example, and then further on with the Fischer-Tropsch, for example, to come to hydrocarbons. The question here is also, does it make sense to use hydrogen as an electricity source? And this, in the end, I said, producing hydrogen only makes sense if we use renewable electricity. So, of course, we have a lot of conversion losses. So, re-electrifying hydrogen to electricity then has more losses. So, it doesn't make sense if you can use the renewable electricity in the first place directly. Okay, so using hydrogen in that sense for as an electricity source only makes sense if you need the storage of electricity in some form. But perhaps in this sense, the message is also we need a constant supply of hydrogen for electrolyzers. There's always the debate of can we use only the so-called intermittent or fluctuating energy in a highly volatile energy system. But of course, you have high capital investments, and if you only wait for the wind to blow or the sun to shine, you will have lots of capital investment sitting idle and waiting. And this, of course, is from a cost perspective very challenging. So yes, perhaps we need energy storage in the future, and in this sense, we also need to discuss how we can maintain or how we can achieve a constant supply of electricity for these processes.
Thank you, Thomas. What is your view? And I would like to add a question which is connected to the hydrogen topic. A question of Frank Halthoff on the chat. How much energy could you substitute by installation of photovoltaic systems?
Well, maybe some words about hydrogen. I fully agree with what Alexis said, but still we maybe should think about where do we get our energy today from? And even if you look on the energy consumption, which is mainly fossil-based in Germany, because you shouldn't look only on the electricity grid. This is maybe 30% of the energy consumption in Germany, but still we are importing more than 90% of our fossil resources to Germany. So why should we think that in the future, if our future maybe is green electricity and maybe green hydrogen, why should we produce that in Germany? I'm pretty sure that you can't do that because we don't have the willingness of the population. And well, to be honest, it's maybe more intelligent to produce or to use photovoltaic modules maybe in the southern part of Europe or in Northern Africa than in Germany. And this is maybe leading a little bit more to our second question. Of course, we thought about to produce renewable energy in the industrial park by windmills or even by photovoltaic, but it's from what we know today, from an economic point of view, not attractive to do so for companies, first of all. And of course, we don't have, even if we have 4.6 square kilometers, that wouldn't fit to fulfill our energetic needs. So this is not enough. Maybe we get some more electricity renewable from our windmills on the North Sea and then the Baltic Sea. But well, then you have to transport the electricity or even maybe hydrogen produced there to the consumers here. And this is possible, from my understanding, if we think about that we have a very wide grid for natural gas. And this could be maybe switched to use to produce or to send hydrogen through these pipelines.
Thank you very much. Maybe in the following discussion, we should focus again on the main topic of this workshop, which is closing the carbon cycle. Alexis, you mentioned and proposed 3 carbon cycles for sustainable chemical industry. Mm. That is biomass using photosynthesis, a natural carbon cycle, recycling, and CO2 use. Could you explain a little more in detail how these cycles differ from each other?
I can try, yes. Perhaps starting with biomass. I was saying that we are also looking at biomass, but in the framework of petrochemicals and base chemicals, which are mainly hydrocarbons, I have to say that the use of biomass is not the most efficient pathway. Because biomass has a lot of useful functional groups, and just putting it down to hydrocarbons in terms of the biomass utilization efficiency is not a very smart idea. So I think if you look at all the concepts of biorefineries, for example, it's a very good idea to keep these functional structures and to do something more useful with biomass and to go directly to some of the special and fine chemicals rather than just doing hydrocarbons from it. So this is the point on biomass. And of course, biomass is a resource which is used for many different purposes. So we have a strong competition when we look at biomass. And I also mentioned the food issue, so the potential competition of agricultural areas for food versus other biomass cultivation. So that much for biomass. For CO2, of course, you can use CO2 in CCU processes. It is an energy demanding process usually, so that's the downside. Essentially, if you look if you compare it with what we are doing today, we're using fossil feedstocks which bring in their own energy. And if you do it with just water and CO2, we have to do everything from scratch. So this is why it's so energy demanding, because CO2 doesn't have any energy content in the end. So we have to bring that in via electricity, and electricity is the most the most valuable form of energy we can think of, and also the most costly. So this is actually where the issue and the challenges arise from, also in terms of the production cost gaps we see when we look at power-to-X technologies. And finally, we have the question of plastic recycling. I mentioned that most of the chemical recycling technologies are still under development. We have to say that. There have been earlier example like Schwarze Pumpe, for example, in Germany that have been operated some time, but that are not anymore in operation today. So there are still challenges with using plastics. You can't do chemical recycling for all types of plastics. PVC, for example, is a challenge because of the chlorine. So there are certain restrictions. So to summarize, perhaps, there's not one technology or one silver bullet pathway where we can solve all of our problems. So we need a portfolio of all these different approaches to come to a greenhouse gas neutral chemical industry in the end.
Yeah, thank you, Alexis. This brings me to a question to Thomas. You are engaged in the BioBall project, which totally focuses on the natural carbon cycle, using biogenic wastes and residuals as a carbon source. From an industrial, from the view of industrial practice, which share can be filled by these kind of carbon sources?
That's a good question. Well, maybe I can argue with Alexis about the figures here, but in any case, don't expect too much, because what we are focusing, and I think Alexis mentioned that, we are not focusing on raw materials from the agricultural side. We are focusing on wastes, meaning that we are thinking in cascades. And I fully agree that we first of all should think to feed the people on Earth. We are focusing more than maybe 10 billion to 11 billion people on Earth soon. So we shouldn't use that in a too high amount for chemical raw materials, but we can focus on wastes. And in this case, well, maybe some percent of the chemical feedstock could be substituted maybe from fossils to renewables if you're using wastes. We shouldn't over expect there too much. But today, even the chemical industry, Alexis mentioned that with about, let's say, 20 million tons of raw materials from organics, the chemical industry in Germany is today using about 30% of that as raw materials like starch or celluloses or something like that. But at the end of the day, well, we maybe can increase that a little bit, but we wouldn't solve our problems because we need a lot of different technologies. And of course, this is why we have in the industrial park our innovation campus to check what kind of, well, part of in the future could these different technologies which are developed today by universities, by startup companies, could bring to the final solution to get to a reduction in the CO2 emissions to zero.
Well, this brings me to the question whether using especially the biogenic carbon sources is only a technology challenge, or whether it's necessary to convince several actors in the region, owners of the materials, and so on. Isn't that an equal challenge to build the infrastructure of owners and actors to make use of these materials?
I think there are a lot of hurdles, and one is still, well, we are not dumping our waste. We have intelligent technical assets to use mainly the waste to produce energy. And we have to shift that. And this is exactly the idea of BioBall, to shift from, let's say, waste to energy, to waste to raw materials. And of course, this is in principle a good idea, but I agree, Manfred, you have to convince people. But at the end of the day, we're not talking about, please shut down your asset today. We're talking about, would it make sense to think about a new kind of technology for the next step, for the next asset? Because normally these plants are running maybe for some decades, and if you have to substitute them, you maybe can think about to use a new kind of technology. And even what is in this end, you have to think about the economy. It has to be attractive to produce something new with new assets. Therefore, the business model has to fit too. So it's a lot of things you have to think about. It's not only availability of wastes, but it's still to think about how could we use it in the best way, and even to, well, get some money out of this.
Yeah, so closing the carbon cycle is a quite complex issue, and this brings me to the podcasts which are published at the moment by BioBall, and I like to make the audience aware of these podcasts. We have published now 3. Another is under preparation, and in these podcasts we discuss closing the carbon cycle from the view of material management. This was a podcast with the Technical University of Darmstadt. Another podcast has been produced addressing food production from biogenic wastes with the University of Gießen. Or another was with the city of Darmstadt, discussing the role of closing the carbon cycle from the view of a city. These are published. You will find these podcasts on our homepage of BioBall. But back to our presentations. Alexis, you presented these three carbon cycles which have potential: biomass, recycling, and CO2. Are these different carbon cycles each valid for all chemical products, or is it to be expected that different carbon cycles will be focused on certain product groups, like basic chemicals or more specialty chemicals?
Well, as I said, probably for the biomass, it's there are smarter ideas than using that for petrochemicals or for hydrocarbons. In the end, the processes that you can deal with are similar. And if you use biomass or plastic waste, for example, if you go to petrochemicals, so this is one difference. Perhaps before I answer your question, I would like one remark to what Thomas also said, because I think this is important. When we talk about closing the carbon cycle, there's one nasty thing we call thermodynamics. We need to always have to keep in the back of our mind. So I'm sure there will always be waste streams which are too complex to do something useful with it. So the use of some waste streams as for energy supply is reasonable and useful. There will be always some waste streams that will need so much energy for conditioning, for separation, and so on, that it's not actually useful to think about it. So in principle, otherwise, if you compare CO2, for example, with chemical recycling, of course you have certain chemical recycling options like solvolysis and depolymerization, which are only useful for some exceptional waste streams or material streams. Other than that, you go back again to building blocks like CO2, for example. And in this sense, there's no difference with the CCU routes in the end. So that's quite similar. Of course, some contra arguments that usually come from some of the environmental organizations in terms of CO2 utilization is always we need to avoid lock-in effects. So typical example, we need CO2 to run our chemical plant. So we need this power plant to operate and to keep burning coal, for example. Of course, this is not what we want. And I said we have some waste streams, industrial waste streams of CO2, that if we want to keep this production in Europe, that will still be there. And that is, well, for cement plants, for example, these emissions are unavoidable. Okay, so we still have this source of CO2. We have some chemical processes where CO2 are available in high purity ammonia production, ethylene oxide production, for example. We have some biotechnological routes where CO2 is generated. We have biogas plants and all these examples. And of course, these are smaller plants, and this again then leads to the question of more decentralized, smaller production plants rather than large world-scale plants with I don't know, 3 to 10,000 tons per day production of methanol. So I think this is the perhaps the paradigm shift we will also have to discuss in the transition of the chemical industry towards these low carbon technologies.
Yeah,
I'm not sure if this answers your question.
It answers, but it provokes new questions.
I guess.
Alexis showed us that this transition is a process for decades to 2050.
Right. I agree.
Well, I ask you as a practitioner, as an industrial practitioner, are we on track? Or if not, how can research, upscaling, and implementation be accelerated? Are there proven models for partnering and technology transfer?
Well, it's a good question if you are on track. My understanding is that the politicians in Brussels and Berlin speeded up their change in the last maybe 2 years. If this is enough or not, you never know. We're going to find positive examples, for example, money for hydrogen technologies, Green Deal on the European Commission, all this stuff. But at the other hand, look on the establishment of new windmills, photovoltaic plants, whatever in Germany to increase our renewable energy. Well, you find positive and negative effects here. So if the chemical industry on track, maybe I can answer it a little bit different. If we want to be carbon neutral in 2050, then we have to think about new technologies today, because assets which are established today are running normally in chemical industry for decades. So you have to think about changes today and maybe establish them starting in 2030, as Alexis mentioned, for example, for new technologies to get methanol out of carbon dioxide and hydrogen. I will give you a really practical example. In my lecture, I showed the example of the Regional Transportation Association, Rhein-Main-Verkehrsverbund. They had to decide last year with which kind of technology they are running the next generation of trains in the region on not electrified routes, because these trains normally running for about 30 years. Yeah. So they had to decide last year if they're running until 2050 with diesel-driven trains or not. And they decided, which is a really high risk, to invest in a new technology because until today, there's only one company producing these trains, and they invented them some years ago. So there's a high technical risk for that. But they asked the question, is it possible to run diesel-fueled trains in 2050 in Germany? And you can argue about that. If the politics will set the rules right and increase the costs for carbon dioxide emissions, you maybe can run diesel-driven trains in these years because it's too expensive. So the same is true for the chemical industry. We have to find decisions, or let's say ways to make decisions within the next years to bring in all the efforts until 2050. And we can't wait until 2040 or 45 or whatever, because in some cases we have to substitute plants within the next years, and they have to run for decades.
This brings me to my last question, which is supported also by Holger Banks. This question is about public acceptance. I think switching diesel trains to hydrogen trains is welcomed by the public, I guess, at least. What about the transition process of the chemical industry? Is it a topic of public awareness, and do you expect public acceptance, or if the public becomes aware of the energy demand of this industry, might there be a problem? What do you think about that?
Well, maybe it's a little bit similar to the discussion we still have in Germany. Yeah. If you're asking the people if they want to have renewable energy, everybody's telling you, well, that's beautiful. If you ask them if they want to have a windmill in front of their house, I know what the answer is. So it's not easy to find the solution therefore. But in any case, in principle, yes, but this is Radio Everyone, right? So you maybe remember that. Of course, we have to work in close handshakes with the public, with the community, with the people, with the politicians. Otherwise, we can't get these, well, very, very high goal of carbon neutral production in 2050.
I totally agree. I would say that perhaps also to your earlier question, we are not lacking public support for research and development and demonstration activities and so on, with Green Deal, with the large hydrogen initiative in Germany, for example, and the lighthouse projects that are coming up. But the framework conditions are still unclear. So how will the electricity price develop? How will the CO2 price develop? How the price of CO2 of fossil resources is very volatile and is of course a demanding factor in terms of competition. So this is something where we need to have clear perspectives for the chemical industry to inform investment decisions in the end, because these are, as Thomas pointed out, decisions that have to be made for decades and large investments. So this is actually something where we need more clarity and more clear perspective for the chemical industry.
Yeah, with that, thank you very much. With that, I would like to close this workshop. The time is over. I think this workshop showed a convincing path into the future of a sustainable chemical industry, including activities and projects currently running, especially here at Frankfurt Höchst. And I'd like to thank very much Alexis Fasanella, Thomas Bayer, and the team in the back office, Christina Andresen and Dorit Lehr. Thank you very much.